Got it. Today's topic, Joyal's lifting theorem. First, some definitions are in order. So recall that a Kant complex is a simplicial set where all horns have fillers. So the horns are the lambda nk horns. And then the quasi-category is a simplicial set where all the inner horns have fillers, where the lower index ranges strictly between 0 and the full dimension. And lastly, a right or left vibration is one where all right or left horns have fillers, where right in this case means that 0 must also the zeroth horn has to have also a filler, similar for, no, sorry, that is I confuse it. The right means that the nth horn has to have a filler, while left means that the 0th has to have a filler. Okay, and with this definitions, we can look what is the homotypic category of a quasi-category. So here are some pictures. Assume that X is a quasi-category, so something where the inner horns are fillers, a simplicial set, and this means that we can look at the edges. In that case, here x1 of x and y are just the edges between x and y, and f and g are two of those, and we say that they are equivalent if they sum of these 4 possible triangles exists, and if one of those exists, then all of them, the existence of all those are equivalent. And these triangles live, of course, in S2 simplex in the simplicial set. And then we can define a category Hx, and the objects of this are the zero simplices of X, and the morphisms are the edges of X, the one simplices, and we quotient out the equivalence relation, which is generated by these equivalences here. And then we can also define a composition. Of course, we must do this for Hx being a category. And this goes like, as indicated in this picture, when we have some f and some g, then this constitutes 2-1 horn. This is the form, how it looks like. And by assumption, since it's a quasi-category, we know that there must be some filler, and in particular, a lower side, which is here D1 of the filler. And this guy this edge shall be the composition. And when you do this definition, then actually this homotypic category will become actual category. And to check that things like associativity works out, there you need to look at a few 3-dimensional horns. And if you can lift the inner 3-dimensional horns, then actually the thing is also associative, this composition. And the identities are given by the degenerate one simplices on a vertex. Okay. Now let's consider a little statement, namely, first we define an isomorphism. So an edge in a quasi-category is called an isomorphism if its corresponding arrow in Hx is just an isomorphism. We have a category Hx, so in the usual sense, it has the same inverse in both directions. And so it generalizes just the normal concept. And then we can say that whenever we have a right vibration between quasi-categories, then call this P from X to Y. Then an isomorphism which starts at a vertex in the image of P and goes to somewhere else. We can always lift it to the domain, namely X. So this guy lives then in Y, of course. And we can lift it to an isomorphism again, now in X. And all this works if P is a right vibration. Why did we do this? Did we need this later for the proof of Joyal's lifting theorem, which I will explain what it actually is after a few definitions we need for the proof and the understanding of the theorem itself. Okay, Well, let's now just give a sketch of the proof. This is not a full proof here, but we can now sketch the proof of this lemma. How does it work? So we know that we can lift all the right horns. In particular, this here is actually a right horn. It's the lambda run horn, the last edge of the interval, the last vertex of the interval. And then we can look at phi inverse, which we assume exists in X because it was an isomorphism. And the diagram altogether commutes because now the inverse ends in P of X of this phi inverse. And then we can get a lift, which goes to X. So we have an X, which maps down via P, this is P, to the isomorph, to the inverse. And this will be a candidate inverse isomorphism on top. And then, okay, we don't have yet the phi itself, but we can just make this construction again, more or less, and also lift or get an inverse of this thing on top itself. So them has to solve a few more lifting problems. I don't dive into this part of the proof. We can, but it's not too difficult, but yeah, a few lifting problems have to be solved, and then you can get an inverse to that inverse and check that actually it's an isomorphism on top and everything works out as desired. Okay, but we want to go to the lifting, Joyal's lifting theorem, which is the main focus. So this is like a little part which we need in the proof, but don't worry too much about it right now. Then let's continue. We want to define, we need to use the so-called join construction to understand the proof of the lifting theorem. And what is the join? So first, consider here the augmented simplex category. These are the finite ordinals with the empty ordinal, which is now denoted as -1, just considered as posets, partially ordered sets. And then we can, because we included the empty ordinal, so -1 here, we can define this monoidal structure, which we just denote by plus, and it adds on this M and N, which are the poset which goes contains all the vertices from 0 to M. So it contains M plus 1 elements, and it maps it to this guy. If you check it, the formula might look strange, but the reason why it looks like that, why we add the +1 here, is just if you count all the vertices, then here you have M plus 1, here you have N plus 1, and then in total you have M plus 1 plus N plus 1, which is exactly how many are in here, how many vertices are in here. And you just put them next to each other and induced maps to get this plus here into a bifunctor. We can just use the maps on the parts. So just put them together next to each other. In particular, it's not symmetric. And we added the -1 to have a unit for this monoidal structure. So this is why we don't use the normal simplex category, but need to use the augmented one. Okay, and when we have this, then we can consider categorically, we can define the join categorically first. Don't worry, there will be an explicit construction later, but first the general procedure which one could always use in such a situation. You take just the left Kahn extension in this diagram, which means it's here we have the Yoneda embeddings here and there, and then you take the somehow initial extension of this guy. Yeah, and this is the join for augmented simplicial sets. And you can also define the join for simplicial sets by first taking the terminal augmentation and then the augmented join. And terminal augmentation means that you have to make give an augmented simplicial set out of a simplicial set. If you get a simplicial set and want to make an augmented one, you just need to define one additional x minus 1. And this is then in this case the terminal set, and there is only one map going into that in the delta plus category, and that's the terminal map. So this is the construction of the join categorically, but you can also do it explicitly, and that's the following. Or geometrically I wrote here, and the idea is that we essentially have this formula. It immediately follows from the last slide. I go back for a minute. Here you have that this square should, in this case, it will actually commute up to isomorphism. So whatever happens on top here, and then they get sent to the standard simplices. So it should, this formula we have here should absolutely hold, that the I simplex and the J simplex join together to the I plus 1 plus J simplex. And pictorially, it looks like this. The join is called like that because we have the two parts here and there, and then we join all the possible edges we add all the possible edges to this, which looks like the normal join of topological spaces. But then you notice that essentially, instead of adding all the edges, it suffices to add just one edge, namely this one, which goes from the last vertex of the standard simplex to the first vertex of the second standard simplex. And all the other ones appear as compositions of anything here and there and this particular edge. And you can also see then the formula, how this join, how the n simplices look like. And this will actually be this. So you have for each pair of simplices in X and Y, such that the dimensions add up correctly, a simplex in the join. For example, when you have this thing and this simplex, then it's a 0 simplex and a 1 simplex, and together they make up this triangle. So essentially, it's more or less the same picture as this, but it lives in itself here a few times. So all the different simplices are just constructed in the same way out of standard simplices. And then we have here this formula, while we just note then that x minus 1, now everything is in terms of simplicial sets. If we would have simplicity augmented this, then this is also the reason why we simplicity augment this stuff. And this is the formula. And you can also give the phase maps, which work like depending on k, whether it is in the first part of the simplex or in the last part of the simplex. Then we just apply the ordinary phase map to the first simplex or the last part, depending on where it is, and if we have to index correctly such that everything works as expected. And then it's just the ordinary operators in this case, for example. And also this induces then also we can do this for the degeneracy maps. So this is the join. First we did it categorically, which by this Khan extension, but now this formula is actually an explicit formula, which is of course very useful. And with this we can draw our pictures, and I have it now. Namely, I call it the combinatorial lemma. And we look at a particular push out join. Namely, this join will be a bifunctor. And when we join the nk horn with the boundary of the M simplex, and then we can include this into on one side each, extending this to either delta M or to delta N here. And then we take the push out. So everything lives in the simplex, and the join of those two simplices, which we already know, is the N plus 1 plus M simplex. So in the pictures we have here, N and M are both 1, and K is 0. And then these pictures arise like that, because if you look a bit at this, then here we have 0, and here we have 0, 1, 2, 0, 1, 2, 3, and here is the 0 horn, and this is the boundary, and then the join will consist of those two guys. And the other pictures are accordingly. Here we have the front face and the last face, the back face, and on here we have the bottom face. And when you glue those together in the push out, this will be everything but the right face. So in this case now I marked it in red, that it's not included in there. Yeah, I have a pen. This is okay. Question to me, whatever. Yeah, my pen is a little bit strange. I don't know. Sometimes it doesn't work as expected. Sorry for this. But okay. Yeah, and this is exactly what the lemma says. Namely, it's this isomorphism that this particular join, push-out join, will give us the kth horn in there. And it's actually true in this case. We have the 0th Dve horn. So this also works in the general case, but again, because it's a little bit combinatorial, I don't go into the proof of that, but I hope the example suffices for convincing you that it actually works, also in the other dimensions. Okay. Then go on to the slice. So what's the slice? The slice, when we have some fixed simplicial set T, and then joining with this does not commute with colimits. For example, if you would do the Cartesian product, then it would commute with colimits, but we do the join and it does not work immediately. You can see this, for example, by considering the initial simplicial set and the join of the empty simplicial set, which is the initial one, with any T is just T again, which means that if T is not initial, then joining with T does not preserve the initial object, so it does not preserve colimits. But it is actually, so T is actually initial in this undercategory of the simplicial sets under T. So if we do that and send X to the map that puts T itself into the last part of this join, then it will actually be will commute with colimits. And whenever you have such a situation, something on simplicial sets that commutes with colimits, then you can just wish yourself a right adjoint, and we call it underslice in this case. We write it like this, and the map Tx, which is an object in T of Sz, T over Sz, goes to this X slice T, and we can calculate the n simplices. This must be by Yoneda lemma, this set of morphisms, delta n to the slice, but by the adjunction, it's the same as these morphisms. And now we are there because nothing that we don't know yet appears here. So this we can take as the definition of the slice. And actually, because the joining, if we change the codomain category to the undercategory under T, then it actually works and will define a right adjoint to joining with T. And similarly, the same idea can be used to get a right adjoint to joining with T on the other side. And then we call it the overslice, since they're written with a backslash. Okay. So all these slices are all very important in the theory of in affinity categories. For example, if you have only one object and consider the nerve, then you can take an object as the image of a map from delta 0 to X. And if the categories are nerves of ordinary one categories, then the nerve of the over category or under category will actually be the slices of the nerves with on the simplicial set side. So this generalizes a bit how this works out with the under and over categories and normal categories. Okay. Yet this does not totally work with general functors. You cannot do the comma category things with this. It's slightly different, but for object it goes through. Okay. Then continue with an adjunction lemma. This is a very important step in the proof we will later employ in Joyal shifting theorem, and namely, when we have a map I that goes from K to L, is now a little bit technical, but bear with me, it will be used over and over, so you will get accustomed, hopefully. So K to L is the map I, S to T is the map J, and X to Y is P. And then when we have in addition a map T to X, then we have a correspondence of these lifting problems. And the left diagram lives under T. So this T here is going in there, and it goes in everything. And using the map to X, which is here, we can also go over there. And well, this corresponds, the lift there, the diagram itself, and also the lift corresponds exactly to each other. And how are these guys actually induced? Well, this map here, this map, can't write, my pen is not recognized always. Okay, now it works. One has to turn it a bit. Yeah, this map is induced by this commutative diagram and going to the push out of this span. And on the other side, this P slice J is induced by this diagram, which is also induced by the same maps and going to the pullback. Well, it's not a little technical lemma that these are actually adjoined. It's not too important now, we won't prove this exactly, but just state the dual lemma instead, which is just everything turned around. Now we use the overslice and yeah, because we have taken the S maps to the other side, and before we had taken K and L. Sorry, we had taken K and L to there, and now it's just S, and everything is then the overslice changes around. But it's not too surprising that these two hold. And for example, if you consider all the maps, then here, for example, we have the T to LX map, and this by adjunction corresponds to this map, for example. And similarly, you have this map, S to L over X, over slice X, then this corresponds to the part on here to X, and so on. Everything corresponds to each other in the appropriate sense. Okay. Now, the main theorem, Joyal's lifting theorem. Now we need to state it and afterwards prove it. Okay, how does it work? Let X be any quasi-category. And then we know that we can lift any horns that have here some K, and K is strictly between 0 and N. But what happens if we want to lift the first guy, so the 0 horn, for example? Then the problem is like this, as it is depicted here, and we can actually lift it, but not always, only if some condition is satisfied. And the condition is that a particular edge in X that is hit by the first guy, the first edge in the horn, is an isomorphism. So it will exactly be the following. So when we have this delta run and write it out in delta run join 0, the empty set I mean, this has a map because you can include the empty set in the boundary of delta n minus 2. It goes to here, and then include everything in this push out. Use the combinatorial lemma to write it as n0, the n0 horn, and then you use the map you have to X. And this defines a simplex in X. If you write it slightly differently, then it's the following simplex, where we have just the 0, 1 edge. So there's a delta 1, and it goes to here, and we can take the 0, 1 edge. Okay, maybe I don't know how to write it. It's the edge that hits the edge between the 0 and the first vertex. It lives in the horn if n is big enough, which it is, because we assume that it's at least 2 nonetheless, because we use this n minus 2 here. Yeah, then this edge has to be an isomorphism. And if that is the case, then it will actually, it is actually possible to lift this, even though we only have as a category. And if we want to maybe lift the nth horn, then this is also okay. We can just go to the opposite category, and then the opposite of n0 will actually be nn. And then you need the condition that not the 0, 1 edge is an isomorphism, but the n minus 1 comma n edge must be an isomorphism if this is n, and then the same idea works out. So I only state the theorem in this way. The dual way is similar, and the proof is of course also as well the same essentially. You can just apply the opposite to everything. Okay. Now we need to do the proof for that theorem. Let's see. So the main proof of the main theorem. By the adjunction lemma, the lifting problem we need to show, so this guy we had here, this lifting problem, is equivalent to this upper square. And now I just tell you and then later explain how the proof actually works. The orange maps, which are here and here, are right vibrations, as we will show later. And now, earlier we have proven that right vibrations are isovibrations. And then it turns out that this theta edge, which is exactly the one we wanted to be an isomorphism, is now an isomorphism down here in X. And it will lift to the top because these are right vibrations. And we prove that exactly the conditions work out in this situation. And this theta lifts again to an isomorphism on top. Yeah, so that's the idea. And now some explanations are in order. How do we actually get this diagram? Yeah. So the upper part of the diagram, which is here, is a special case of a diagram we have already seen, namely in the adjunction lemma, which looked like this. But we have to put in the correct entries. So we have put in the correct values for s and t and y and x and everything. And in this case, we take the inclusion of s to t to be this guy. So the boundary of delta n minus 2 into the whole standard simplex, and y is the point. If we do that, then here the pullback along the point and the slice with point, if y is a point, then this guy is also a point. So this totally vanishes, and we are left with x slice t and x slice s, which is in this case exactly what we want. So this is how the upper diagram is constructed. And very similar to that, the lower part is constructed as well. So this is the lower part of the main proof. And now we just have to again take y equals 0, then this is not there. And s has to be 0 as well. Now we take this inclusion for the inclusion of s to t, and the empty set, I mean. And I will say 0, I meant the y is terminal and s is initial, and then the slice with s being the empty simplicial set will be just x, and then we get this diagram. And again, so everything reduces to essentially proving that in general those p slice j maps are right vibrations. So we want to prove that they are right vibrations. And in order to do that, we can just restrict ourselves to the general case of p slice j, and we need to show that this is a right vibration. And if we have that, then by the first lemma we had on the second slide or something, then theta will lift to the top, and the lifting theorem of by Joyal is proven. Okay. So in order to show that this P slice J is actually a right vibration, we give us exactly the diagram which we need to use this. So again, here is it. We need to show that this Pj is a right vibration. I just stated again the proposition we need to show, and the corollary of this, that the proof works out. Okay, then let's tackle the problem. We take us a right Horn inclusion, which is here. So 0 is less than k and less or equal to n. And we need to show that in a general situation, commutative square, as in this picture, with the Pj map on the right, then there is always a lift. Now, the first thing we can do is we use the adjunction lemma from before to transform this diagram into this one. The whole lifting problem is transformed to this one, and it's equivalent to the one on the right, on the left. And now we copy this left-hand side to here and adjoin it back. But now we use the dual adjunction lemma because here, instead of considering this under T, so usually this diagram lives in T over simplicial sets. But in this special case, we can actually just consider this in delta n under simplicial sets. Because delta n and T just live on the first, on the upper left corner of the diagram, and the other maps just need to be decompositions with the one we already have given. So the lifting condition is it's not necessary to consider this in either of these ones. It's just not relevant. So we can just now use actually the dual adjunction lemma and put now the delta n's to the other side. And now we have this S to T here. And now again, we copy the right-hand side to the left. And now we use that S to T was actually assumed to be a monomorphism. We only need to apply this to the case of monomorphisms, and this is also the situation we now only can, because we want to make the crucial reduction step in this step now. And the step is that instead of considering all the possible monomorphisms, all the problem for all possible monomorphisms, it just suffices to consider it for the generating ones, and these are the boundary inclusions. So it suffices to just solve all kinds of these lifting problems. Now it's much easier since there's no general S and T anymore. And again, now using the adjunction lemma, putting everything back gives us this situation. And this is the perfect situation where we now can apply the combinatorial lemma. And this means that the map on the left is exactly the Horn inclusion of the kth n+1 plus m Horn in the n+1 plus m simplex. And because now 0 is less than k and less or equal than n, this will actually be an inner Horn. It's well, obviously k is bigger than 0, and also the +1 is here, so it will be an inner Horn. And now everything is perfect because we also assume that P is an inner vibration, and then we are done. So we can now lift this and in total prove that the Pj map is always a right vibration, which solves the lifting problem, so which gives the proof of the lifting problem of Joyal. Okay. Now, after we've now done seen the problem itself, so the theorem itself, now we can do some applications, and I will give a few applications. So the canonical application is probably this one. This is also why the theorem was invented. And so back then, when Joyal thought of this theorem, the idea was that quasi-category, which is a Kant complex, should exactly be the same as a groupoid and as an infinity groupoid. So quasi-categories are infinity categories, and groupoids are the infinity. So Kant complexes will be the infinity groupoids in there. And now we have the theorem that Hx is a groupoid, which means that all the edges are isomorphisms, all the arrows are isomorphisms, if and only if X is a Kant complex. So if you, for example, consider this in the basic case when you have only a two-horn, then it's easy to see that this condition must certainly be, for example, let's draw one two-horn, this guy, and this. This is a lifting problem, and if now, sorry, this, here's some f, here we can take the identity, and when we now can find and lift a filler for that, it's necessarily an inverse of f. And similarly, when we consider the other side, we can consider always the lift with the, the lift with the identity, and a filler will always be an inverse. So this is absolutely necessary that we must be able to lift the two-dimensional horns. But the amazing thing of the lifting theorem is then that it solves all the difficulties with lifting all the higher horns. There are quite many combinatorial intricacies going on, and now we have solved them all, and just have seen that essentially the question whether one particular edge has a specific property, namely being an isomorphism in this case. This implies that all higher horns that have this edge as on a particular spot are also fillable. And now this means, let's just go through this proof of this corollary. So one direction of this is obvious, namely the one when we have a Kant complex, then it's a groupoid. This is the argument I just drew here, that the two horns can be lifted. And the other direction follows by Joyal's lifting theorem, because we only need to show, because we already assume that it's a quasi-category, so only the outer horns are left to be filled. And all these outer horns, they are fillable if the particular edge is an isomorphism, but we assume that all the edges are isomorphisms, so it works. And then we can additionally check the one-dimensional case, but it obviously works as well. Okay, and that's the idea of this corollary. And also the motivation why quasi-categories came back into use, mainly with the paper by Joyal, which proved the lifting theorem. Okay, and now another corollary or another application. Okay, no, not a corollary, first a definition. After that, an application. Namely, we define what the core of a quasi-category should be. So usually in run categories, one can consider the core, and this is just taking the subgroup, the maximal subgroup, right? And now we're doing essentially the same thing. So we consider the simplicial subset that consists of all simplices, with all edges being isomorphisms. And when we can write it like this, I didn't say this. Actually, this H, sorry, I didn't say this. Actually, H is adjoint to N. You can also define the H for all simplicial sets, while N is the nerve of a category. I didn't say this earlier, but it holds. And then if you take the unit here, which here and there, no, not there, okay, here. Here's the unit of this adjunction. And then what it means is here, the nerve of the core of the homogeneous category. This gives you, it's used by HX core to HX. And this is the ordinary groupoid core on categories, where you just take all the edges, which are isomorphisms, and then you take the nerve to make it, give it back into, go back to a simplicial sets. But in total, this guy has the description. It's just a subset in here and in X. and it consists of all the simplices such that all the edges of those simplices are isomorphisms. Okay, and another description of this, it is the biggest Kant complex contained in X. By Joyal's lifting theorem, it is actually a Kant complex because we only need to check that edges are isomorphisms. And then any map from a Kant complex factors then to this X column. Okay. Then let's go on to the application again of this core and also in essence of Joyal's lifting theorem, namely the characterization of isomorphisms. So when we have any edge in a quasi-category, this is an isomorphism if and only if it comes from such factorization. So we can look at the nerve of the category J, where J is thus just this guy, and may call it the walking isomorphism, where we have some two objects and two morphisms, phi and its inverse. And the edge in the quasi-category is known as isomorphism if and only if it comes from a map from Nj, where then this delta 1 is included into, well, it's not important in which we include it, but let's just include it in phi in this picture now. Okay, and description of Nj of the simplices, there are only two non-degenerate simplices in Nj, namely, we recall that the simplex, the simplices in the nerve are the sequences of n-fold possible n-fold edges in the category. So we go around and we can stay in theory at an identity and then go back and whatever we can do, we can make an n-fold possible composition. So a string of arrows that fit together. But if we want to have them non-degenerate, it means we may not stay at a vertex for too long, but always move immediately back to the other one. And then there are exactly two non-degenerate simplices, namely the one starting at 0 and the one starting at 1. And then alternating between those two, where we can call this maybe 0 and this one. Okay, and now interesting, this is a side remark, not totally related to this, but it's interesting, I think, just to know that the geometric realization of the nerve of the J category is the infinity sphere. And this also gives a proof that the infinity sphere is contractible because J itself is equivalent to the terminal category. And nerve and realization both preserve, well, they said natural transformations, essentially then in the end to homotopies. And because this category being contractible is essentially the condition that if you think of natural transformations as homotopies, which is possible, then it's like contractible in categories. So this is a rather slick proof, if you know the theory of the nerves and so on, that the infinity sphere is contractible. Interesting, but it's not too important for the theorem. We just now want to go to the proof of this proposition that all the isomorphisms can be characterized in this way. So now on to the proof. And the idea is we make a filtration of the nerve of J and then show that each step, it is essentially an outer horn that we have attached. Okay. JK shall be the simplicial subset that is generated by the K simplex, which let's just say it starts at 0. We could also start at 1, it's not important, but now let's just take this one. It consists, has this simplex and all the possible faces and degeneracies of it. So everything we can get from there. And this simplicial subset fits with the previous ones into such a push out here. I do not explain explicitly why this actually works, but just believe me that this actually works out. One can check it on the simplicity set level and just looking at all the simplices of the appearing simplicity sets here. And then it turns out that this is a push out. And now if you have an isomorphism, then by the description of the core, X core, this isomorphism will factor through that. And because we only attached these guys, so the delta, the lambda n 0, so the outer horns, we attach only outer horns. This means that or in total, nj also lifts to this X core, which means then that the whole map can be extended to nj. So the isomorphism factors through that. A backwards direction would be easier. If some map factors through the nerf of j, then it must be by functoriality again be an isomorphism. So that is obvious. But now this is of course the more difficult backwards direction. Or forwards direction, whatever. Okay. So let's look at it. So this was the characterization of isomorphisms. And it is also possible to give the folklore theorem that object-wise, that natural isomorphisms can be characterized object-wise. So this is the last thing I will now present, and it's a little proof, which is adapted from the book by Sisinski. And we want to express the well-known statement for one categories that when you have an isomorphism as a natural transformation, so a natural isomorphism, then in order to check that it's a natural isomorphism, you can just look at all the components, and if they are all invertible, then it's an isomorphism. This is rather obvious for the one categorical case, but in infinity category, it's a bit more difficult, of course, because there is also higher stuff happening. Yeah, so usually one would say that a transformation is invertible if there is a transformation in the backwards direction, but it lives in the functor category from x to y and y to x then, and we can compose them. And then the question is this composed a composed transformation, which is a one simplex of this functor category, equivalent to the identity? And there you need to have also consider higher horns, which is a bit difficult, but in total it works out, which we will see now. But first, define the object of object-wise invertibles. So we do it as follows. When we have a simple set x, then we can consider x0 to be the constant simplicial set on the vertices of it. And then we have here pullback functors that just look at what the functor on top does on all the vertices. And to say that a functor is object-wise an isomorphism means, a natural transformation is object-wise an isomorphism, just means that we consider this sub-category of the functor category x to y, which contains all those transformations. It contains all the functors, but it only contains all the transformations that are object-wise isomorphisms. So one could say that it is like a right subcategory, contains all the objects, but not all the morphisms. And then the statement which we want for the object-wise criterion is when we have this thing which we defined here by pullback. It's actually the same as if we take the functor category, which is again a quasi-category, and consider the quasi-categorical core of it. So the core just flips from here to there. And yeah, this theorem gives us then this characterization of object-wise natural isomorphisms. this gives us the characterization of natural isomorphisms, which is the object-wise criterion. Okay. And now the last lemma before we prove that is this one by Sisinski in his book. It's theorem 3.5.8. And we now define to state it first h of x, y, which is somehow similar to the object-wise invertibles of x and y, or x and z in this case. And we define it by the proposed existence of such an adjunction. So we have flipped around the x and the y. And if this adjunction holds, we can also describe both of these guys explicitly, namely this as well as this h will be a simplicial subset of the functor category, functors from x from y to z or x to z, whatever. But it's slightly different because this is a right subcategory where we take all the functors and only the object-wise invertibles as transformations, and then whatever we must do for making it a simplicial set. And on here, we take the full subcategory, essentially, of those functors that send all the simplices in Y, the one simplices in Y, to isomorphisms. So this depends really on Y. Well, so when we have some edge in Y, then this should go to an isomorphism in Z by some functor. But we take essentially all the transformations. Okay, so if we have this existence of a natural isomorphism, then these will be the descriptions of these two sites. Sorry. Then if Y is a quasi-category, then the evaluation at the one object, the last the codomain of this delta one category, has the right lifting property against monomorphisms that induce a projection on objects. So a different way to state that is to state that it has the right lifting property to these kind of maps. So essentially the same as we had for monomorphisms, but we only consider the n bigger than 0 part. And if n is greater than 0, then we can only, we must stay constant. So it does not change, it does not add any vertices. So everything which is in the saturated class of these guys will again be a bijection on objects. The only possibility to add a vertex is by considering the case n equals 0, where the top part is empty and the bottom part is a point. Then we can add a point. But now we don't do that, and so we need to check that all these problems admit lifts for the lemma here. So we prove it now, or at least give a sketch. I don't know. Now we don't do it completely. It's a little bit sketched, but not too bad, probably. So again, just copy the statement and now the proof. How it goes further. So when we we get a lift in the last diagram by analyzing this has to be deleted by analyzing a few inner horns and one outer horn in the end. And inner horns we can always lift, and outer horns can be lifted using Joyal's lifting theorem if the particular edge is an isomorphism. So wait, there's probably a diagram missing. Yeah. So it's a little strange. I just what? We would look at this delta n cross delta 1 union delta n cross 1. So they last, so the one object, one pointed set, then we go to y, and then here it goes to delta n cross delta 1. So this whole thing will be the diagram and the lift here we need to do to get. And then we still need to check that everything also goes through here. So this would be the diagram if the h would be replaced by functors. And then you would use a special case of the adjunction lemma. And this would then yield exactly the diagram I drew before. Yeah, I forgot to draw this diagram here. But yeah, to show this all, that in the diagram I drew here, that this works, this delta n cross delta 1 simplicity set which appeared here has specific description how it can be constructed out of the product push out, which was on top. And then we have to add a few horns and simplices that are still missing. But most of them are inner horns, and the last one will be an outer horn. And there we have to use Joyal's lifting theorem, and to show that then the particular edge which works out, this must be then isomorphism, but in this case it will be. I don't go into the details why this actually holds, but again, it's you could also read it in the book by Sosinski. There a bit more of this to that is written down. But well, if this works out, then we just need to show that the horn we would get, if that would be replaced, this h would be replaced, if this was replaced by the functor category, then this would work, but we actually want the h here. So what we now need to check as well is we look at this diagram, which is again a pullback, because if you look at the map, then delta n and the boundary of this, they are in bijection on the one simplices. And by definition, all these two, the object-wise invertibles, are both defined by pullback along a map that stays constant on the one simplices. So if we go to here again, we had both times x0 here. And then we have taken a pullback to define the object-wise invertibles. And because here nothing changes on x0, this diagram will again be a pullback. And to check that something, so this simplex, so this guy lives in here, so this actually goes through the age of something, of delta 1 to y. We can equivalently consider this in here. So the condition that the simplex, this defines essentially one simplex in this category, because the 1 corresponds to maps from delta 1 into that, and then you can interchange the delta 1 and the delta n, and then this corresponds to the map we have here. And because we have the core here, we will have the h on the previous slide, and then everything works out. And so in essence, you need to check that everything comes from here and from here. And this does work because in the diagram, we have this map already going to h. And also the last part does not have any conditions. This is this part. And here on this side, we do not have any conditions on any map going to an isomorphism. It just works out by the construction. And then we can actually show that on the one simplices, it will live in the correct thing, and it will be an isomorphism. The edges that need to be an isomorphism work out. And in total, you show that this evaluation at the first edge will have the right lifting property against, first of all, first of all the inclusions of these standard simplices, the boundaries for n bigger than 0, but then also just on all inclusions, monomorphisms that induce a bijection on objects. Okay, and using that, we can go on to the last part of the proof, namely that now the functor category, the object-wise invertibles, is the same as the core of the functor category. So one inclusion is rather obvious, namely the one written down here. If something is in the core, then of course all the evaluations will be isomorphisms. And to show the other direction, it suffices to show that this guy is actually a Kahn complex. If this holds, then because the core is the biggest Kahn complex, they will actually be equal. So this is what we need to show, that this is a Kahn complex. Hence, again, by a little application of Joyal's lifting theorem, it essentially suffices to prove that it is a left Kahn complex. If we can do that, for proving that it's a Kahn complex, we need to show that it's a quasi-category, which it is, and secondly, that all the edges are isomorphisms. And for that, we can even consider only the two-dimensional case. It already suffices in theory. And when we consider the two-dimensional case, we need to show that when we have that it's a left Kahn complex, then we can also show that it's a right Kahn complex, because the question is whether we can lift all the isomorphisms, whether everything is an isomorphism. And while doing a left inverse of a left inverse will actually be the same as the original map. This is always the case. You can prove this in this context, again, using lifting some horns. And this is the idea here, why we only need to consider the case for left Kahn complexes. And now we take, again, a little redescribing the problem. Namely, left Kahn complexes are equivalently characterized by not only by the left horns inclusions, but we could also consider these kind of inclusions. So the reason why we have left now is because of the 1. If this was a 0, then this would be a right Kahn complex. Then this would check for this condition. But essentially, if these are quasi-categories, then those two notions are the same. So because it's a quasi-category, we now can essentially restrict to this situation. We need to show that in here, this always exists. Okay, then let's take the whole diagram. So that this goes to here and adjoin it again. So what we do is we put the delta 1 over to the other side, and the x goes over here. And when we do that, then the outer diagram will correspond to the top outer diagram, and the lift from here to here correspond to the lifts correspond to here. So those two kinds of lifts correspond to each other. And then in the end, one needs to check that it actually goes through this part as well, which again, a little technical, but let's first consider what happens down here. So in this picture, because this is an inclusion, if n equals 0, that's the point, then the original problem is easy to solve. There's no problem then. So this is then just just delta 1 cross, what is it? 1 cross delta n, which is 0. So it's just an additional point. So there's no problem if you do that, and it just works out. if n is bigger than 0, then we will have a bijection on objects here. So this will be a bijection on objects. And this means by the previous, so the last lemma, and now I use last as previous. You may be surprised because in the last slide I used, may have thought that I would have used last as the last lemma of the talk. One might also say the ultimate lemma, which is the last one, but this in time idea of time. But now it's just the previous one. So double meaning of last here. Well, this is just a joke. Don't ignore that just for now. And yeah, using that, we can show that here the lift exists. Yeah, in this case, when it's bigger than 0. Now we have this lift and we are almost done. We now need to check that given this lift, then the lift, of course, we have also a composition to here. And this first just corresponds to this guy. And now to again see that this actually goes to here, we look at two diagrams again, and namely here. So what we need to do is we rewrite it a bit, and the lift is characterized by such a map. And we need to show that it goes through the object-wise invertibles. And this happens if and only if it only hits isomorphisms after evaluating any object. So we consider this diagram here. This is a picture of delta 1 cross delta n, and then embedded into into y, because we evaluated also at an x in the object of x of the simplicial set x. And then we need to see that all the things that appear here, so all the things here are all isomorphisms. So first, those ones are isomorphisms. We have here, because when we restrict the lift to delta 1 across delta n, the boundary of delta n, which is in particular this, then this will be will factor over the object-wise invertibles. So there it works. And again, when we restrict it to run cross delta n, then these ones will be isomorphisms. But this actually suffices. So in total, everything which we see, also the arrows which are not drawn, everything is an isomorphism. And that's the proof of the statement. So the map we had here, which went to there, actually corresponds to something here, and now it also factors through here. Okay. Are there any questions? Because now I'm done with the topics. It's a bit early. I was told that it's 90 minutes. I thought it would be a bit less, but okay. We can ask many questions then, and yeah. Okay, no one asked questions. Should we stop the recording somehow?
If there are no questions.